Okay.
Tell us all about the process.
So the creation of deuterium in the plasma of the sun, the plasma of the sun consisted mostly of protons, and due to the high energy, they're whizzing around really fast, and occasionally two protons will stick together to form deuterium, which is hydrogen with one proton, one neutron. The one proton remains a proton, and the other one becomes a neutron, and an electron is emitted, and that is the creation of deuterium.
And is there also energy released in this process?
There is a little bit of energy released, but not that.
Not a whole lot. So it's not an important part of the process, but there is some released.
Yeah.
Okay. All right. Okay. So your process is?
Creation of tritium.
How's it work?
Lots of pressure comes about, and then the regular hydrogen isotope smashes into deuterium.
Deuterium. And what do you mean by regular hydrogen? It is the most common form.
Yeah.
Because
it's stable.
Because it is stable.
Yeah.
What's it made of?
Protons.
Just a proton, right? No extra neutron. Okay, keep going. And those two smash into each other. Really high pressures because they're really high what?
Temperature.
Temperatures. And what do you get?
You get tritium, which is a slightly radioactive form of hydrogen and a little bit of energy.
And is that energy an important part of the process?
Yes.
Yes,
It
because...
gives off heat.
And that heat does what for the sun or the nuclear bomb or the...
It fuels the explosion.
Fuels the continuation of this whole process, right?
Yeah. Hey Frank, so your tritium fusion, how does this whole process work?
Well, two deuterium atoms come together to form tritium and a proton and a bunch of energy.
Because what's deuterium?
It's a isotope of hydrogen where one proton, one neutron.
And then you have tritium, which is...
Another isotope of hydrogen, less common, two neutrons, one proton.
And then what are the results of that fusion?
The results are a tritium and a proton and energy.
Why does it emit a proton?
Because there is a extra proton from the two deuterium atoms that fuse. So you miss that proton, which can then combine with another proton to form another deuterium atom.
So the process can continue elsewhere in the star, right?
Yes.
And then you also end up with what? What's that E?
That E is energy. You get about 4 mega electron volts worth of energy out of this fusion.
Okay, so is the goal to get energy out?
Yes.
And that energy comes from what?
It comes from the two deuterium atoms coming together and smashing together to form these other
And
outcomes.
so what is lost to give you energy? Einstein's super famous equation. What is it?
Some mass.
You're losing mass. You're losing mass to gain energy, and that's what's happening.
Then, if you have deuterium and another one of your hydrogens, you can create helium-3, which consists of 2 protons and 1 neutron. And that emits more energy than just the deuterium creation, but it is not the best way to create helium-3. That would be with deuterium and tritium, but this is just one method.
And does this method actually happen in our fusion reactors that we're trying to build?
I mean, it can happen. We don't even have fusion reactors, so no fusion can happen.
Well, we don't have fusion reactors that can actually put out extra energy, but we are actually fusing things. We're just not doing it well. So we have this helium-3, and then that helium-3 can be used for?
Can be used to
In the sun, for?
in the sun to create helium-4,
So it can be used over here.
which is the creation of helium-4 with helium-3 and deuterium.
So in the process of making this, what are we making here?
Helium-3.
Helium-3. What is helium-3?
It's helium with 2 protons and a neutron.
And how do you know it's helium?
2 protons.
Because it has 2 protons, and all heliums always have 2 protons, right?
Yeah.
It's one of those what's of helium?
Isotopes.
Isotopes. And how do we make helium-3 in the sun?
You put 2 deuterium together, and then you get a
Come on.
helium-3,
You have helium-3 and
a neutron, and energy.
energy. And what's the most important part of that process? Well, there are 2 really important parts.
What do you mean? Important.
There are 2 important, very important components of results of that process. What's like
Energy.
energy? We want energy for what purpose?
Like our cars, lights and
Eventually, if we can use that, but where is this usually happening?
the sun.
This is happening in the sun. So why does the sun want the energy? Not that it has desires, because it doesn't, but heat. For what purpose in the sun?
Fusing more stuff together.
Fusing more stuff together. That's exactly it. And is that helium-3 used for something else?
Eventually to make like carbon.
Eventually to make carbon, and in the next step, it's to make what?
Helium-4.
Helium-4. Got the beauty happening. Okay. All right, now let's. You're describing for us helium-4 fusion. What's another name for helium-4? What kind of particle is that?
It's a noble gas.
Yeah, but what kind of particle? This is a nuclear decay particle. 2 protons, 2 neutrons. What is it?
alpha.
Alpha particle. Yes. Okay. Describe this process.
Deuterium and tritium fuse together to form helium and a neutron and a lot of energy.
And so, what's deuterium?
1 proton and 1 neutron.
1 proton, 1 neutron, and tritium is,
1 proton and 2 neutrons.
and they are both isotopes of.
Hydrogen.
And then you put them together, you get helium. And what's the most important part of this process?
You get energy.
That you get energy. And that, so what does that energy actually do?
That's a good question.
Where is the alternate name for that helium-4 particle?
Alpha.
It's called an alpha particle now. Okay, so describe this helium-4 fusion process. What's happening?
Alright, so you have hydrogen,
You need point 2.
hydrogen,
What kind of hydrogen?
hydrogen 2.
Hydrogen 2 has what particles in it?
It has 1 proton and 1 electron. It's neutron.
Proton and electron. You have
No.
electrons in the nucleus here? Because these are
Nope.
nuclei, right? Okay, there's 1 proton,
Proton.
1 neutron.
Yep.
And?
That's it.
And
Oh, and then you have the helium,
it's put together with helium.
which has
Which
2
helium?
protons and 1 neutron.
And that's called helium what?
3.
It's a helium-3 because it has 3 nucleons, right?
Yep.
And then you get what?
And then it yields helium-4,
Helium-4.
which has 2 protons and 2 neutrons.
Also known as a what particle?
Alpha,
Alpha particle. And then you also get what other things?
helium-1,
Which is also known as a what? It's pink. It's a what?
oh, protons.
It's proton. And you get what else?
And it emits energy.
Emits energy. And is that an important part of this process?
Yes.
Okay, why is that an important part of this process?
Because the point was to get more energy out of the initial thing.
Out of this whole process, right?
Than
So
what
the
we
point
put
is
in.
to get more energy out than you put in, and in this case, ultimately you get helium-4 out plus a bunch of energy. This is just a beauty pose right here.
Okay.
Okay, so now this particular process that is in black, because we see the other ones are in purple and yellow. Did you choose black?
Yes.
And why did you choose black?
Because it's carbon and forms of carbon, such as coal, graphite, or black.
Nice, good, black. So when does this process actually happen in our star?
It happens kind of as the star contracts down, it creates more heat and pressure, and then it re-expands out as energy and gets reignited from a different fusion process.
All right, so it's a new fusion process, not the fusion process that's happening in our star right now, correct?
No.
Okay, so describe what's happening here.
Two alpha particles, or helium nuclei, that can shoot from the electrons because the plasma fuse together to become beryllium-8. Now, this doesn't stay around very long because another helium nuclei comes and connects with that to form a 12-6 carbon.
Okay, so carbon with carbon always has nice design, by the way. Carbon always has how many protons?
6.
And in this case, it has how many neutrons?
12.
And will our star fuse bigger than this?
Yes, eventually.
And what will it eventually fuse?
It will eventually start fusing heavier elements until it gets to iron.
Up to iron, but iron's the biggest?
Up until it dies.
Okay, so iron's the biggest, and it'll keep on fusing until it dies. And will it actually do all of these processes that we see here until it dies?
Yes, but some become much more rare than we do on Earth. For example, tritium fusion doesn't happen as often in stars as we would have it happen on Earth.
Okay. Because?
Because we like using tritium for fusion reactors because you get a much higher energy curve from it. But it takes a neutron to do tritium as an entry product, while deuterium is just 2 protons. So it's more likely you get more deuterium than tritium in a star.
All right. Thank you.